Hi, we'd like to welcome you to another in a series of webinars designed for departments of transportation. I'm Terry Bills, and I'm the Transportation Industry Manager here at Esri, and today I'm joined by Alberto Nieto, a solutions engineer on our federal and transportation sales team. Today's webinar is focused on how departments of transportation can utilize GIS together with machine learning solutions and artificial intelligence to gain greater insight and knowledge from their digital data. As you'll see, we're just beginning to understand the myriad of ways in which we can apply these new technologies to address critical transportation issues. Before we begin, I'd like to point out that we are recording this webinar, and while everyone will be on mute, there'll be time for question and answers at the end of the presentation. And you can type your questions into the question box, and we'll try to answer as many as time allows. Additionally, the slides which are part of this webinar will be available to you on the GeoNet group, Departments of Transportation, and we'll give you that link at the end of the webinar. All right, so to begin, a few years ago, two researchers at MIT forecast the future of these emerging technologies, calling it the second machine age. They forecast that through the use of machine learning and the ability to use AI to develop sophisticated algorithms, that the modern age would allow us to build systems that would be able to better manage our modern systems than what humans on their own would be able to accomplish. And while there are wide-ranging forecasts, both positive and negative, about the impact of artificial intelligence, today we want to focus on some very practical applications for machine learning and AI in transportation. And as you will see, there are a wide range of transportation issues that can be addressed with these technologies. One of the early areas that we applied machine learning was in safety analysis. The ability to apply machine learning to a large amount of crash and infrastructure data allowed us to look at crash prediction capabilities, as well as to better understand patterns in our crash data. And Alberto will speak to some of that work that he's been doing for NHTSA in the webinar. We ultimately think that we're just beginning to scratch the surface of how these technologies could be applied to help safety researchers better understand crash factors and to help design safer and more forgiving roadways. A key area of research for us is looking at how we can use machine learning to do feature extraction, whether moving or static features. So you'll see these technologies applied to pedestrian and vehicle classification and the various ways such applications could be used. And these are already being put into practice in a number of jurisdictions. And again, we think we're just beginning to a whole new area of research there. And on the more static features, the ability to extract transportation features from digital videos for asset collection and asset condition is just beginning, but we feel holds great promise. Alberto has done some preliminary work on using machine learning for pavement condition analysis. We think the use of machine learning and AI for better maintenance analysis and prediction is an area we all should be quite interested in. And finally, as we move into autonomous and connected vehicles, it's clear that these technologies will play an ever bigger role in helping to manage our future traffic systems. The ability to train our adaptive signal control systems will likely shepherd in a whole new era of traffic management systems, allowing us to better manage our future urban traffic. But with that, let me turn it over to Alberto, who will give you some background both on what machine learning and AI is, but also how it can be applied in the context of the ArcGIS platform. So, Alberto, over to you.
Excellent. Thank you so much, Terry. So we'll start with a brief view, and actually, let me confirm that you can see my screen. Can you see my screen at this point?
Not yet.
Okay.
I can see it, Alberto.
Oh, okay. All right.
Okay,
Go
great.
ahead.
Thank you. So we'd briefly like to start kind of with an explanation about what machine learning is and kind of tackle a lot of the buzzwords that you see, not just through technology companies like ourselves, but also through marketing, through advertising, through literature, through academia, etc. It's fair to say that it's one of the most important technologies that you'll probably come across in this year and the coming years, and it's the use of it and the propagation of these terms is only going to grow, right? So as GIS professionals, as transportation professionals, it's incumbent upon us to explore these concepts and see what's actually useful and understand basically where the tangible concepts are that tie to what you do every day, right? And generally speaking, what we'd like to do is break down these problems into maybe just three terms to begin with, starting with artificial intelligence at the broadest level, take a look at a subset of artificial intelligence, which we define as machine learning, or which we refer to as machine learning. And then briefly speaking, these new concepts related to deep learning, or concepts that have become popular if they're not entirely new. And we see machine learning and deep learning as subsets of AI. And even though AI itself is kind of this inspiring and deeply interesting concept and phenomenon, where you can have computers and processes try to emulate what people do to get information or to perform some type of to achieve some goal. I think the focus of our discussions and the focus of what we do every day as professionals should really be on machine learning, not so much on AI itself, right? And what I mean by machine learning is essentially data-driven algorithms or techniques that learn from data to give you information, right? And they automate that process to get that information from the data and to get you the information that you need. I think it's fair to say that it's not a new technique. It's something that has been around for decades, but it's this interesting mix of large amounts of compute power available at any individual's fingertips and large amounts of data that organizations are collecting. And that mix of a lot of data, a lot of compute is kind of merging into the need for new systems to better extract information. And that has been around for a long time, but in the past 5 years or so, it's where the compute and data mix together to make individuals and small organizations be able to do this enough. What we're trying to do recently is understand how spatial machine learning actually can be useful. So to incorporate geography in the computation of these processes, right? And it's not just to use geography as this disparate field to join different data sets together. It's actually to introduce geography in the inherent computation. So computing the shape of some phenomena, the density, the spatial distribution, the proximity, the distances, etc. And those features or those explanatory factors can be very useful when you try to get information from some data set. And also Esri is looking into advancing our own processes and our own tools to be computationally intensive and to be performant when you're trying to tackle these types of problems because of the large amounts of data. So again, we're looking at machine learning from the perspective of the typical organization or analyst that works with this, right? And there's a lot of different tools. So a lot of those buzzwords that you saw in the beginning about things like TensorFlow or CNTK and scikit-learn, these are tools or frameworks that people use today to build these solutions that learn from data to get information, right? And it's fair to say that something that's missing here is ArcGIS. We have a variety of tools that we've put into our platform over the years to add machine learning algorithms. We may not be loud about this. We may not broadly advertise that we're a machine learning company, but we put it in the ways that are intended to help the analyst or the person performing the data science at its most inherent. So for instance, there's tools that perform classification that have been popular for some time, perhaps to perform land cover classification or to do pixel level classification, right? There's new tools related to clustering, and we'll get into those. If you understand the spatial distribution of some phenomena, that can be very important as you start to understand that phenomena or to prioritize where you should pay attention to. And then obviously there's prediction, which is quite easy to understand, if not difficult to perform. And prediction is seen as a very important facet of our integration with machine learning. obviously the development of models and understanding a phenomena well enough that you can bring explanatory factors to predict in some unknown location or at some unknown time step in your data is very important. But we'd like to kind of really also insert machine learning in elegant ways, in my view. So for instance, when you open up a geoprocessing tool, and the geoprocessing tool provides you all these parameters that you entered, but when you specify the data input and it sets automatically what the other parameters should be, that's a way to learn from your data what the parameters of this analysis should be so that the analyst doesn't have to. In my view, that's a very elegant integration of machine learning that is not flashy, it's not marketable necessarily, but it is important and it helps people do analysis better. So there's a variety of ways that we've brought machine learning into ArcGIS over the years. And I think it's worth to actually take a look at some of these examples today. Now, we've talked about machine learning, but we haven't really touched on deep learning. With deep learning, there's these newer concepts of being adaptive, right? So I think the example that I always like to consider with deep learning is that some people have smart home speakers, right? Like Amazon Alexa or Google Home. And with these smart home speakers, you typically speak to it like a person. You just ask it, what is the weather today? Or what is my traffic like going to work? And the speaker hopefully gives you the answer, right? But you can speak to it with a different accent. I will butcher the English language when I ask about the weather, but it typically still manages to give me an answer back. Or I can speak to it in very imprecise ways. I can say, what is the weather like today? Or I can restate that sentence in a slightly different way, and it's still able to infer what I'm asking, right? So deep learning is about being adaptive, about not hard coding this process to a series of, not making a SQL query out of your question to a smart home speaker, but actually just speaking like a person. And the tool at play, or the framework at play, that allows that adaptability is this concept of a neural network. And we will briefly talk about neural networks, but that concept is definitely a bit more technical, and I suggest that you take a look at additional workshops that we perhaps host that can deal with that. What I would like to say with respect to deep learning is that we facilitate integration with external frameworks that do this. So we're not going to have all the development resources to bring every single neural network algorithm into ArcGIS, at least not yet. But if you do happen to have some capability that you need integrated for your solution, for instance, the detection of pedestrian activity in a web camera, and if that's important to your organization, we're going to integrate with algorithms that let you do that. And I'll show you examples of how to do that. So this story, this part of our work with deep learning really is about giving you the right APIs, the application programming interfaces, to let you do that conversation, right? To integrate with some solution that perhaps you built outside in TensorFlow or scikit-learn to perform that detection of people in webcams and then speak back to the GIS system of record. So again, if we look back at that word cloud of terms, I think it is fair to introduce ArcGIS into that. And also I would advise you to pay attention to what is actually useful from those terms, right? And even though we do start with this word cloud, I think what's most important ultimately is what question are you trying to answer? If you always look up literature and blog posts and information about how to do this, a lot of people talk about starting with data, then feature engineering, performing analysis, et cetera. And that's all definitely valid. But one crucial step that is often missing is that first step of ask a question or determine what your organization's goals are broadly and how you fit into that, and then ask a question that actually needs answering. If it happens to need machine learning, that is great. There's awesome ways to do that. If it doesn't, then great too. I think machine learning is a tool that can be used. It doesn't have to be used, right? So what we're going to do today is take a look at a few different demonstrations. And the demonstrations are going to be broken down into these three types of problems. Problems related to classification, clustering, and prediction, which we briefly talked about. Let's start with classification. And the way I kind of think about classification is that you've built this history of understanding what observations should belong to, right? Let's say that you care about pedestrian activity. And you know that you can classify pedestrian activity in terms of it being dense or sparse. Those are two classes that new observations can belong to, right? And the way that you can have a system do this for you so that a person doesn't have to do this manually is an interesting integration of machine learning. So we're going to start with taking a look at classifying pedestrian activity. And this is actually an example that we're collaborating with Cobb County outside of Atlanta, Georgia. So let's go over to our application here. So what you're seeing is a operations dashboard, and let me move my controller here briefly. Here on the map on the right side, you see a view of SunTrust Park, which is a new baseball stadium that was recently completed. And this baseball park is kind of interesting. It's not the traditional layout that you see in most cities. It's not near acres of parking spaces. It's actually in a mixed-use development with a lot of restaurants, a lot of shopping areas, etc. To get to the parking areas, people have to traverse this path highlighted in green, and eventually they make their way across to the parking areas where they probably parked and make their way home. So what's interesting about this is that essentially and let me expand this map actually to make it a bit easier to see. As people are coming across this path, in the first intersection, 30,000 people suddenly leave the stadium. The first intersection is well handled by this pedestrian bridge. People make their way across this bridge and then decide where to go from there. But eventually, the pedestrians are going to start interacting with the vehicle traffic, particularly at this intersection. And this can be quite tricky for the transportation authorities and for the police department there to handle. I'm going to show you an example. So this dashboard gives us a sense of the activity over the span of an hour from 4 p.m. to 5 p.m. on a day in which we knew there was a baseball game. I'm going to zoom into minute 53 here. And in this minute, I am aware that the people are already starting to bunch up here at the end of our path. And if I select this image, it'll load here in a moment, you actually see the pedestrian crowd starting to take over the intersection, which is necessary. Essentially, people sit in front of dashboard cameras or in front of webcams that monitor the situation, and they'll initiate what they call a scramble, which is when they stop traffic in all sides and they let the pedestrians cross safely to clear the situation, right? So this is done manually today. Essentially, if we look at how they perform this operation today, they have people sitting in an operations room with views of these three cameras, camera 128 at the beginning, 129 at the second part, and 130 at the end. And then once the situation gets busy enough, then they'll radio into the police patrol that's at that third intersection, at the last intersection rather, and they'll ask them to stop traffic in all directions and initiate that scramble. But what they asked us to do is to automate that process of designating whether activity in these three cameras is dense, medium, or sparse at any given minute. And we were able to do that. In this case, we did it with an integration with IBM Watson. The way it started is we took several snapshots of the three cameras, essentially static JPEGs and PNGs, several hundred of them, and we asked the police department there to classify these manually to tell us if they would consider this given activity sparse or dense or medium. And after several iterations and interviews with the police department there, we had that training data that we were able to use with IBM Watson to train new classifiers, new models essentially to perform that detection over time. So this dashboard shows the automated classification over the span of this hour. Looking back at the beginning of the hour, most activity was pretty sparse. So basically these are 10-second intervals that we're showing. This is before the game ends, nothing too crazy so far. Now, fast forward about 30 minutes. Let's go to minute 37, let's say. And people are starting to emerge the stadium. And now we're starting to automatically classify this activity as dense. So the people are leaving the stadium, starting to make their way across that area. And we're gathering data on pedestrian activity automatically through the model. The model processes the imagery, gives us the dense classification. And then fast forward a few more minutes, probably about 15 minutes for that crowd to make their way across that path to camera 130. And once again, you saw the image earlier of the crowds eventually landing at that intersection, initiating the scramble, right? So in my view, and actually from the feedback that we received from Cobb County, this was quite important for a number of reasons. One, it's very good to capture real-time data. So they're starting to put this process into play for new events. At the next baseball game, they will run these algorithms to classify. They will have this web application showing them the real-time activity. And then they can set up notifications, right? So if camera 128 remains dense for some amount of time, let's say 5 minutes straight of dense activity, of dense pedestrian activity specifically, then that can send a notification to their devices, to their phones, or through email, through any type of notification system to initiate the operations, right? They don't need to be sitting there in front of these cameras for the whole duration of the event. And so that's one aspect in which it can help, real-time notification. The second aspect in which it can help is actually monitoring and reviewing an event and determining how successful they were at managing this event. So if you think about it, compare the amount of time at which camera 128 and 129 remain dense to the amount of time that camera 130 remains dense, and that can be a metric to determine how successful the last intersection was handled. So if this intersection is dense for a longer period of time, that can signify that an issue happened or that the scrambles didn't initiate at the right times, and this situation was significantly worse than the other two places. And as it turns out, we learned that they do a pretty good job of handling the situation because it's consistently about the same amount of time for 130. So that's one brief example, and in that case, it's integration with IBM Watson to perform pedestrian activity classification. Another example is object detection. So what we did previously is just classify images wholesale. We pass it a new frame from a video, and it tells us whether pedestrian activity, broadly speaking, is dense, medium, or sparse, right? In this next example, I'm going to show you. So let's expand this. And this is a traffic camera in Jackson Hole, Wyoming, looking at this intersection live right now. And there's vehicles, obviously, that you're able to detect with your own eyes and brain without knowing what every vehicle looks like. And there could be pedestrians, or there could be, generic types of activity that we can detect. And the idea here is we want to, once again, use an operations dashboard to try to capture that real-time activity. So this is the dashboard before we kick off the process. It's a simple map, and then a few charts to show some typical activity such as cars, amounts of large trucks, buses, motorcycles, etc. And to execute this, and a lot of what we do behind the scenes, the engine that runs this is Python typically, specifically the ArcGIS API for Python, integrating with some external framework like TensorFlow or IBM Watson in the previous example. What I'm going to do is kind of position everything and leave it ready to see everything in action. So briefly here, we're going to see the detection of that model's kick off. There we go. And then this dashboard is going to update about every 6 seconds. So this is a prototype, of course. This is not perfect, but it is meant to kind of help us understand the proof of concept, how we can iterate and refine and start to detect different types of objects. So as this vehicle starts to make its way across the intersection, we can try to classify it and provide that type of real-time view through the operations dashboard. And the way this actually becomes more tangible with organizations is when we start to think about capturing trends, right? Or comparing the real-time view to some historic view of the intersection. And another aspect of object detection that I can actually share is what Terry briefly mentioned in the beginning with the exciting world of asphalt distress types, right? So many folks may work with this type of data with pavement cracks, essentially. And I was new to this workload for sure, but I'm coming to understand these types of distresses. Obviously, these are just 3 of the several types of distresses, but we're trying to focus on these 3 classes. And the idea here is that there's several organizations, not just in the US, but worldwide, that capture a lot of data on the condition of the transportation networks, and they do this manually. They often, the one use case at the US Department of Transportation that I'm aware of is a team of two approach where people get in a van, drive down, or visually infer where pavement distress marker and some dimensions or specifics about each distress. That is important, but very monotonous work. And there's a lot of turnover in that team, unfortunately. A lot of brilliant people leave that team that hopefully get a chance to do analysis or to use this data for work, right? So what we wanted to see is how we could put this into play, this concept of detecting a specific type of object and build that data as automatically as much as we can. Try organizing. There's a simple smartphone attached to a device. And once again, we're gonna shift gears here over to a Jupyter notebook to some Python code that references, once we start detecting objects, the labels for D0, D01, D10, etc. Those are going to correspond to specific types of distresses. And without further ado, let me go ahead and kick it off, and we're going to take a look at what that looks like. Okay, and then we're going to hit play and bring our model view back up. So you see an inset here. This is a real-time view of what the model sees in my screen. And as the vehicle starts to move, you're going to see different types of distresses or objects, right, being detected in the frames of the image, or the frames of the video, rather. And it's an automated process that actually it's adapted for fast imagery. So even if the camera speeds up, even if the recording speeds up, rather, it's still able to infer and find quite a few of these features. And as this is processing, as the vehicle makes its way across the bridge and across the tunnel, we want to build a system of record, a baseline data set of this. So I'm going to minimize these two aspects here, and we're going to navigate over to a dashboard. And that dashboard, actually, let's go over to it right over here. Please bear with me. We're going to load our dashboard here. And I love operations dashboards simply because they let me quickly visualize the outputs of some of this analysis, right? I don't need to know JavaScript or HTML or CSS or what of that data. So this is a view of that data set, of the data set that we've put together from that process of detecting objects. And what we're showing here on the map is essentially a very simple view of longitudinal cracks where the size of the point represents more faults, right? If we zoom in and click a specific feature, then we can take a look at some of the inferred or the inference from the model. And then the charts here are meant to symbolize and help you kind of discover patterns in a specific region. Something interesting and definitely caveats that you should keep in mind, and best practices that we're starting to build as we keep working with this, is the model is decent to good at detecting specific types of cracks, so longitudinal cracks and alligator cracks, but it's not very good at finding lateral cracks. So a best practice that we're starting to propagate is local models are better than global models. So the more specific you can make a model for any given purpose, the better. For instance, in the SunTrust Park Stadium example, we had 3 discrete models for each camera along that pedestrian pathway. And that's because that's the only way we were able to improve the accuracy of the model enough. And building models is quite fast these days. It's improving the accuracy that takes a lot of time, or finding enough training data that takes a lot of time. So that's a brief best practice. Try to localize your models as much as you can for your given purpose, especially since it's fast to build models these days. So this is another brief example, right? of classification and specifically object detection for collecting data. Now, the next problem case doesn't have to do with classification, doesn't have to do with an understanding of what things should belong to. In this example, we're going to group data by the natural patterns in the data without knowing what it should belong to. And clustering is a bit closer in nature to what a typical analyst does, in my view. I think most analysts don't have the final answer or even a history of answers to draw upon to say what something should belong to. They're going to try to just explore their data set and try to figure out the inherent pattern in their data. And that's very, very important, obviously. I think the one example that I always reference when I think about clustering is Netflix. A lot of people consume Netflix. They'll watch different shows, different movies. And Netflix, as an organization, they want to understand what the different groups of viewers are so that they can know what they should market to you, right? So they'll cluster you into a group. If you happen to like scary movies or action movies, they'll cluster you into that group so that they know that the next suggestion should be relevant to your cluster, to your group. And in geography, that's tremendously important. It's almost obvious, right? So the first example that I'm going to show you is actually pretty basic in nature, but I think still powerful. This is exploring patterns of fatal vehicle accidents in conjunction with NHTSA and with the FARS dataset. So we're going to open up ArcGIS Pro in this case, and this is a highlight of some of the tools that we have in our ArcGIS Pro software to let you do machine learning from this client without needing to know how to code. So what you're seeing is a data set of fatal accidents over the span of 1 year, about 36,000 points. And what we want to try to ask, the question we're trying to answer is, where are the locations where we find enough density of events that we should target for further analysis or that we should consider for further resources or for some type of safety measure, right? And clustering is a perfect example to use here. So what I'm going to use is a geoprocessing tool called DensityBased Clustering. This tool, broadly speaking, what it does is it takes an input point data set and it separates it into clusters or noise. And that can be a very useful first step whenever you're trying to understand the distribution of some data. Typically, when I receive some new data set, if it's vector, if it's points or discrete features, one of the first things I do is I cluster and I just try to get a sense of where the spatial distribution portrays clustering in some area. And in this example, we're going to leverage that input point data set. We're going to signify what our output features should be. And then there's a few different types of clustering methods because it signifies 3 algorithms that we've put into this tool. One algorithm is called dbScan, and briefly speaking, what dbScan lets you do is really be specific with what you mean by a cluster. In this case, I mean that I want at least 3 fatal accidents in my cluster, and that for the search distance, I'm going to specify that I care about 1,000 feet in the logic. If I run this, it's actually pretty fast. It's going to boil this data set down to just about 65 locations that could be the targets of further analysis, right? Now, before we actually dive a bit deeper into this, I do implore you to take a look at the other algorithms. There's an algorithm called HDBScan, which actually makes some of the parameters disappear. And this is where the machine learning really comes into play. HDBScan is really good if you want the algorithm to determine what an appropriate search distance is for your run. That can be important if you're trying to delineate the difference, for instance, between urban environments and rural environments. A cluster in New York City is going to be quite different from a cluster in rural Florida, right? So you don't want to define that for every single state in your first pass, perhaps. Maybe if you're doing some detailed analysis, you do. But if you just want to explore quickly, HEBScan is really powerful to do that, and that'll define a cluster for each region. Okay, so back to this. We now have just 65 locations roughly that came back as being pertinent. Now, these locations, there's several components, several discrete fatal accidents that contributed to each location. And what we could do is query the data and find the clusters that have homogeneous first harm events. And what I mean by that is I want to find the clusters where every single fatal accident was caused by the same type of event, such as a vehicle hitting a pedestrian or a vehicle hitting a tree or another vehicle at high speed. If I do that, it boils down that data set down to just about 7 discrete locations. And that's just exploration, right? This isn't a terribly complex analysis, but it's just exploring our data and the spatial distribution using clustering. And something that I always am intrigued by is if we zoom into one of these locations and turn on satellite imagery, we actually start to see some interesting patterns. This one pattern is of a truck stop outside of Dallas in a rural road. And there are no streetlights here to manage this situation. So that could be an interesting situation to try to take a look at in a bit closer fashion. And this was pretty quick to find using clustering. Of course, clustering is not generally the final answer to some problem, but it can be the very good start to getting to that final answer. Another brief view of clustering happens to be also with the US Department of Transportation, specifically with the Bureau of Transportation Statistics. In this case, what we're trying to do is take a look at AIS data. AIS corresponds to GPS breadcrumbs from marine vessels. And what we're looking at here is basically just a specific UTM zone's worth of AIS data for 1 month. And what the Bureau of Transportation Statistics is trying to do is create a data set of ferry routes, of data-driven ferry routes. They want it to be updated on a very frequent basis, and they want AIS to inform that data set. So something that they can do is they can filter out any specific vessel. So if I turn this on and I turn my animation, we query for one vessel. We see that this vessel goes from Staten Island to the southern tip of New York. This is the Staten Island ferry. And if we plot this route over the span of that 1 month, even though the typical path is that straight line shot from Staten Island to Battery Park, sometimes the ferry takes this abnormal route, right? Sometimes maybe the ferry has to linger for some time, or there could be something that causes the ferry to take the route south of Governor's Island. So if we take a look at this data and we try to understand what is the typical path that Staten Island ferry takes as it makes its journeys, you can visually perceive that, right? I could visually do some manual querying and filter out these abnormal routes. You kind of get a sense of what the typical path is. Or you can do clustering to try to infer what the typical path is. And if you do density-based clustering in this case, you're left with essentially a lot of points that are part of a cluster and a lot of points that are part of noise. And if we query out that noise, we essentially eliminate those abnormal routes that the Staten Island ferry sometimes takes. And then this can be passed to another generalizing function to make that ferry route polyline for that data set. So this is kind of a step in their process to start creating these ferry routes. It's again, clustering can be a good component of a larger process, right? Not terribly complex, nothing that requires an advanced degree or anything like that, but it is about automating things that are a bit tougher to automate in traditional sense. So these are a couple of views of clustering, and my suggestion, again, just from previous work, is using density-based clustering for vector point data sets is a pretty interesting way to just gain a basic understanding of the spatial distribution of your data. Now we're going to switch gears to our final problem case, and this final problem case is the holy grail, I think, by a lot of organizations, prediction, right? And a lot of people kind of start here. And my suggestion would be that this is really the final piece to analysis, or the long-term aspirations of an analysis would be to understand some phenomena so well that you can assume to predict it in unknown locations or unknown times. So you need to really build up to prediction, typically speaking. And what I want to demonstrate here today is not necessarily tied to transportation directly, but I hope you can make some connections to the work that you do. My background is actually on financial analysis, and we do a lot, or I used to do, before joining Esri, I used to do a lot of forecasting for real estate models. So a lot of different factors leading up to the price of some property or some commercial venue, right? And the tool I'd like to show today does use transportation data to determine what the home sale value should be in a parcel in a county in Ohio. And once again, this is an example of machine learning in ArcGIS Pro. So we're going to take a quick trip over to Summit County, Ohio. And this is a county that includes Akron, Ohio, and a suburb of Cleveland, Ohio. This county has, we have some data for all the parcels in the county. So if we zoom in a bit closer, you see all the different parcels. For each parcel, we have information pertaining to the information about the home at the parcel. So if we scroll down here, we see the year that the home was built, the amount of rooms in the home, the bedrooms, bathrooms, etc. And for a subset of these, we have also the home sale value. So let's say that we did a survey in Summit County, Ohio, and we collected home sale values for the parcels in blue. Not all of the parcels, but just a subset. I would say it's about 10% of all the parcels we have home sale values. So we need to build a model that will predict the home sale value for all the parcels using this training data from the survey, right? So how would you do that? If you look up a lot of guides online, or if you look up documentation or blog posts about how to build models to predict something like this, a lot of people will tell you that you need to do feature engineering. And along with feature engineering, a lot of the examples take a look at the attributes of each home, like the amount of rooms it has, the year the home was built, the square footage of the home. And those are definitely important factors when you think about home sale prices, right? But very few of those machine learning examples talk about location, ironically. Very few of those aspects think about, okay, what are the characteristics of Summit County of Ohio? And we are going to take a look at those things very briefly. So I'm going to bring in some explanatory variables. We're going to start with golf courses. Let's think about how the proximity to golf courses for all of the parcels matters. We're also going to take a look at railroads. This is a true brief side note. My wife's family is from Ohio, and over the holidays, actually in a few weeks, I will be traveling to Ohio to stay there. And every night at around 2 a.m., there's a train that passes pretty close to their house and wakes the entire house up. Or actually, it woke me up. They're used to it at this point. It rattles the house. So the proximity to these railroads matters a great deal when you're thinking about the standard of living for homes in Ohio, as it turns out. Proximity to highway noise walls could be important, or proximity to major highways. And the way we're going to actually incorporate the distances for every single parcel to all of these features in ArcGIS Pro is with a tool. The tool is called Forest-Based Classification and Regression, and we're going to take a look at a previous run of the tool. So forest-based classification and regression is a geoprocessing tool. When you open up the tool, it's basically meant to incorporate an algorithm in machine learning called random forest. Random forest is about breaking up your problem into discrete decisions that the algorithm needs to make. So it'll find these patterns in your data and all the explanatory features to help you predict, essentially. And in this tool, there's 3 ways in which we can bring in explanatory factors to help predict. The first thing that you can incorporate is training variables, and this is the attribute data in your table. So let's say the amount of base, or whether the home has a basement or not, how many bedrooms the home has, the square footage of the home, how many bathrooms, etc. You can bring in these features for sure, but we can also bring in explanatory training distance features, and this is how we calculate the distances between every single parcel in our data, all of these individual discrete polygons, and every feature that we've brought in as a distance factor, right? So to give you a view of how the tool calculates that, let's take a look at some layers. So the tool will calculate this for you. It'll figure out, okay, for golf courses, for example, here's all the parcels symbolized by the distance to the nearest golf course. Here's all the parcels symbolized by the distance to the nearest railroad. Here's all the parcels symbolized by the distance to the nearest highway. And similarly, here's all the parcels symbolized by the distance to the nearest noise wall. The tool will do this for you. And if you look at the attribute table from the output, it'll give you a distance for every single parcel to those features. And those distances can be really, really important when you predict. And finally, there's one more way to pass explanatory features, which is training raster. So let's say that elevation matters to determine the home sale value. I could bring in a raster with a digital elevation model, a DEM, and incorporate that, and it'll simply compute what's the elevation at any given parcel. That could be important. For this example, it's not, so I'm leaving it blank. And what's important here is I've run this tool twice. I've run this tool for one aspect in which, if we take a look here, we bring in those explanatory training distances. And if you run regression, if you do predictive modeling, one of the ways in which you can explain how effective the model is using your R squared. R squared basically explains how much of the variability in home sale prices can be explained by the explanatory factors that we've provided. So here, the regression diagnostics say that given all of those features, the attributes and the distance features, we can explain 95% of the variability in home sale prices with those factors. And if we look at the outputs, here's what the model says. So the homes in darker green essentially are more expensive. The homes in lighter green are less expensive. And this is essentially the model assigning a home sale value to all parcels using our training data and those explanatory factors. So within ArcGIS, you can build a model, a machine learning model, in this case, a random forest model, and you can pass explanatory factors in a variety of ways. You can use the attribute table and know the different characteristics of each home. You can use distance features and the proximities of your features to other events or other phenomena. And this can be an effective way to think about predicting and modeling without having to know how to code. Of course, these tools can be programmed against, and if you would rather code, you can use ArcPy or the ArcGIS API for Python to automate this. Okay. So that's my final demonstration. And again, it's not quite directly related to transportation, but you can hopefully think of some connections to your domains and to the problems that you face in your organization that could benefit from prediction and modeling. And also rest assured that the tools incorporate robust algorithms, complex algorithms, but they're simple to run by design. And it's about thinking of that as our product, right? It's the ability to run complex algorithms in a simple and effective manner to let you leverage that domain expertise as quickly as possible. So again, we've covered a lot, and we started with this cloud of buzzwords and different things that you will probably see in commercials and conversations, etc. But really what I, again, want to emphasize is what question are you trying to answer? What are you focusing on? Because that's where we would love to learn. Hopefully some of these concepts relate to what you're doing, but we would love to open up the conversation to learn about you. Thank you so much.
All right, thanks, Alberto. Again, just a reminder, you can type in your questions in the question box, and we'll take the time to answer as many as we can. So to begin, Alberto, what would be the best way for someone to really get started with machine learning? You've sort of gone over a number of the techniques, a number of the tools. Is there really what's the best place to start, or the best way to start?
My suggestion is to look up in Google something called the language of spatial analysis. And you will see the first entry here is a PDF. And the reason we start with this is because machine learning is a tool that can be used when you perform analysis. But the concepts of performing analysis are still relevant. If the idea is typically not to do machine learning, right? The idea is not to create a neural network. I don't think people are looking to build neural networks. They're looking to answer questions. They're looking to classify pedestrian activity, or they're looking to detect automatically where pavement distresses are, or to build a predictive model because they want to answer some question. And this PDF takes you along this progression of how to do analysis. I think this is something good to start with before you get to the point where you think about predicting or before using machine learning. So briefly speaking, there's a segment here that talks about the 6 categories of spatial analysis, where you understand where phenomena is, you start performing measurements, you determine how things are related. And machine learning will naturally come into play when you get to the final pieces here, when you start trying to detect and quantify the patterns that you see in your data. For instance, with clustering, we're trying to measure how strong is the statistical significance of some clustering of fatal accidents, right? And we're trying to understand how those things compare so that we can prioritize. Or for prediction, if we're trying to say that given some policy change, what would be the predicted outcome? If we lower the speed limit in this highway segment, how will that lead to some change in the modeling? Or how will the model interpret the eventual fatal accidents in that segment? That's when machine learning naturally starts to become an option, right? But before you get to that point, all of these fundamental pieces are still tremendously important. Having good data that establishes where your phenomena is. Something that we often do is we show you these final demonstrations of the final analysis product, right? But something that we should probably start doing is showing you the process beginning to end and how much data cleanup has to happen, how many fundamental questions have to be answered, right? And I think that this is a good place to start this PDF.
Okay, so there is a question basically along with the geoprocessing tools that you illustrated and you mentioned here. Are these all entirely within ArcGIS, or are there some outside platforms as well? So you did mention obviously the use of Watson, and maybe you could just kind of briefly discuss some of the other platforms that you referenced.
Yeah, absolutely. So many of the tools are in ArcGIS. I showed you a couple of examples. We took a look at clustering, and to do that, I leveraged a tool that you can find, for example, in spatial statistics, mapping clusters, called DensityBased Clustering. This is in ArcGIS Pro as of version 2.2. We also use, for the home cell prediction example, we used a tool called forest-based classification and regression. Again, you can find that in spatial statistics under modeling, modeling spatial relationships, forest-based classification and regression. Those are tools in ArcGIS Pro. But for some other examples, like the classification examples, we used external tools. And in that case, the one integration that I did, for instance, for the detection of activity in Jackson Hole was a tool called TensorFlow, or a framework called TensorFlow. This is open source, and you don't have to pay to use it. You just basically install a Python module. And the tricky part with integration is typically just thinking about how to format the inputs to this framework. So pass the frames from the image or the video to this tool, and then have it give you the outputs that you can bring back into ArcGIS, right? So this is one example. TensorFlow is one example. Another example is IBM Watson, which we use for the stadium example here. IBM Watson does provide a little bit of an easier on-ramp, I would say, than TensorFlow. TensorFlow, you need to be pretty well used to Python and to working with heavy Python modules. IBM Watson provides you a GUI that lets you build models using essentially drag and drop mechanisms and through a web interface. So there's a lot of options, and I would say depending on your level of comfort with Python and with APIs in general, that may determine which option you should go with. And also it's very problem dependent. One brief thing also to elaborate on this question, whenever you think about integration, for example, with the pavement distress example, there's 3 main steps that you generally go through. You start with labeled data. I think we briefly talked about that when we looked at SunTrust Spark. There's the training process, which does happen outside and it's very platform dependent. With TensorFlow, it would be a process to take your inputs and put them in the right format to train a TensorFlow model. With IBM Watson, is going to be different. But finally, when you bring it back in, I would definitely suggest that everyone take a look at the ArcGIS API for Python, which kind of orchestrates the whole operation.
Okay, thanks, Alberto. There was another question really having to do with what Python libraries are you using for the image analysis and video analysis?
Generally speaking, I use TensorFlow and the TensorFlow Object Detection API. And those are for the object detection examples, meaning when we draw bounding boxes on imagery or on video feeds, that's TensorFlow Object Detection API. The other example that I showed is IBM Watson, and IBM Watson has classifying or classifiers that you can build. This isn't for bounding box, this is for image wholesale classification, where you just want to say this image pertains to this class.
All right. And let's see. In terms of the spatial components that the ArcGIS adds to these, to Watson and to TensorFlow, could you briefly speak about kind of what you're going to be able to uncover that you would not be able to without using ArcGIS?
So with ArcGIS, there's a few different ways in which the integration with ArcGIS, I think, benefits you if you are looking to do object detection or to do pixel level classification, for instance. And those we didn't really cover today. I think we can probably consider them for an upcoming webinar. But there's actually this view is the best way to think about that. To create an object detection model, you need to start with labeled data. And to create labeled data, you need to look at static images and draw bounding boxes or to signify somewhere in that image where the phenomena that you care about is. And we have a tool in ArcGIS that was released as of 2.2, if I'm not mistaken. I'm going to try to find it here, called Export Training Data for Deep Learning. So if you look at Image Analyst, Segmentation and Classification, Export Training Data for Deep Learning. This tool is typically meant to facilitate classification workflows for aerial imagery or for satellite imagery. So it has its specific use cases, but if you're trying to apply object detection for the identification of, for instance, flooding in transportation networks or impediments in transportation networks, that could be relevant. And the way you would label your data to make your training data set is, let's say that you have a feature class or a shapefile of your objects that you care about. Let's say an impediment on the road, a tree falling on the road. You can digitize that as a polygon. And if you have enough representative examples and you have a raster, if you have imagery that shows that in play, then you can use this tool to create your training data. What it'll give you is this output format. It can be something called Kitty, or it can be Pascal Visual Object Classes. These are two deep learning formats for input training data. Then when you get to TensorFlow, you're going to take that and pass it to your TensorFlow training process. We didn't really get into the training process. That's actually quite a bit of a deeper talk. But what TensorFlow will expect is training data in a specified format. That GP tool helps you put that together. And then the second half of this equation is that once you have this model that's ready to detect or to infer a new imagery, then there's an upcoming tool, an upcoming geoprocessing tool called Detect Objects Using Deep Learning. It's kind of like the last part. So now that you've built this model in TensorFlow or externally, you can bring it back into ArcGIS, pass it a new raster, pass it a reference to your model, and then it'll digitize the features in some unknown imagery, right? So that's one aspect of several that I can think of in which ArcGIS kind of helps this integration. Perhaps the final thing that I can say here is that many organizations use their GIS as their system of record. So ultimately, any information that you are able to extract out of the data needs to make its way to your system of record. If that's GIS, then ArcGIS is, and the tools, the API, et cetera, are how you bring that back in.
Okay, thanks. A couple of related questions. One, basically, can we use these tools with remote sensing data like LiDAR? And if so, what tools would we use for remote sensing analysis?
Yeah, that's a great broad question. I would say there's a whole discipline that you can start to take a look at there. It depends really on the problem you're trying to solve, right? So we have I think learn.arcgis.com, if I'm not mistaken, has a series of lessons, and some of them do start to take a look at performing remote sensing workflows. There's also literature, and there's also training that we provide if you are looking to get started with remote sensing workflows. At a broad level, I would ask you to take a look at learn.arcgis.com and at our training curriculum. Once you get past that, then I think I Googled just training, not training ArcGIS. Perhaps we can find that. Yeah, Esri training. There we go. So take a look at these two resources, learn.arcgis.com and esri.com/training. We do have a series of courses and curriculum that is built specifically for remote sensing. Once you've made it to that point where you know how to do it with the standalone tools, and you do look for further integration, perhaps with something like TensorFlow, if you are looking to do it, or LiDAR, for instance, then connect with us. Honestly, the best way to try to figure out how to solve a problem is to reach out to us at Esri. We'll try to understand the problem with you and learn together and figure it out.
Okay, thanks, Alberto. And unfortunately, that's all the time that we have today. Again, feel free to reach out to either Alberto or myself with any further questions. We hope that you've enjoyed this. And as I said, we really think that this is going to open up a whole new realm for the way in which ArcGIS can be used to help solve transportation problems. So with that, thank you for attending, and we look forward to having you on a future webinars. Okay, bye-bye.